Hello and welcome, folks, to 2023 Advent of Code Day 10. So, safe to say that this has been the most difficult problem of it so far for me. I tied myself up in a whole bunch of knots on two different little bits in it. One of them kind of ended up being, one of them was a simple enough fix. The other one took me a while to get my head around. I was just missing one tiny little bit. I knew once I figured out what that was, then I'd have the solution, but it took me ages to figure that out. So yeah, this was pretty tough. And yeah, with that said, let's just jump straight in. Talk about the problem, talk about the code, because I'm done thinking about this problem. To be perfectly honest, for today. Okay, so day 10, pipe maze. So we use our hang glider to ride up on the hot air from the desert all the way up to this floating metal island. So yeah, you say you find that it's cold up there. There's no more thermals to glide on, so you land your glider, and you start wandering around. Everything's made of metal, flowers, trees, and so suddenly you hear something. You see something scuttle away, and it jumps into a big pipe. So you look around you and you realize that what you've been walking on the ground is a whole massive big network of pipes, and you want to basically try and map out so you sketch out a map of this whole pipe network, which is the input for our puzzle. And the basic idea is, you're given a start point on this map, and you need to navigate your way through this network of pipes. What we're told is that it basically seems like there's a big old loop of this pipe network creates a big old loop. So from our start point, we're supposed to basically walk through the whole network of pipes till we get back around to the start again. Well, don't have to do that, but this is the way I've inferred it, is basically we determine the whole length of the entire loop, in which case like each one is like a step we're going through, so we count all of our steps. And what we're told is we want to try and find the furthest away point from the start inside the loop. So because we're told it's a loop, you know that at some point as you go around the loop, you'll start coming back on yourself, so you'll start getting closer to yourself again. So if you were to just walk the entire loop and count how many steps it took you to walk the entire loop, half of that would be basically your answer. So that would be half of it would get you to your middle point, and then that'll be your answer, because that's as far away as you can get from the start. So for example, we have down here, we've got, say, this one here, so where we have our start point here. So no matter which way we go, because we're told it's a loop, we'll take 1, 2, 3, 4, 5, 6, 7, 8 steps to get back to the start again. So if we start here, we do 1 step, 2 steps, 3 steps, 4 steps. We know that that's going to be our answer because it's that many steps to get around. Because as soon as we start walking back the way, we're going to be getting closer to ourselves. So the answer is half of the overall length. So if it's an even number, then it's half. If it's an odd number, then it'll be half. It'll be half rounded up plus 1 to give you the right answer. Yeah, that's it really. We're given all these symbols, which kind of makes it's a little difficult to parse it, but it's not super complicated. So they're kind of obvious what they are. You have a vertical pipe, horizontal pipe, and then you've got these 4 90 degrees. You've got dots, which mean basically nothing there, and then you've got S, which is just a single S that you'll have in your input, which is your starting position. And that effectively, you can think of that as being a pipe that's open in all directions, so you can travel from there in any way. Yeah, so that's it. So the first thing you're basically going to need to do in this exercise is you're going to have to figure out a way of parsing the whole map and modeling it in some way. And you're going to need to be able to interpret each of these pipe connections, basically. So it's all well and good to say we just have to walk this path, but you need to be able to figure out how they're connected. So from any one starting point, you need to be able to know how do you get to the next one, and then how do you get to the next one on from that, and so on and so forth. So I came up with a method for doing it. As I'm thinking about it now, it's probably not a very good method, but we'll go through it all the same. So yeah, that's about it. He gives a lot of examples in this of how to get there, but let's just jump into the code anyway and see if we can make sense of it. So, okay, so first things first. I decided to create this, basically this lookup up here of all of the different types of nodes that we'll encounter, and the lookup basically defines the connection points to this. So each of these pipes basically has two bits to it. It has like an input part and an output part, and they model what the shape of that is. So what I've done is I've made this array of 4 values. This would be similar to how CSS would define, say, the borders of a box. So effectively what I've said is this is looking at the left, then there's the top, and then there's the right, and then there's the bottom as you go along this list. So false in this instance means that you can't get into this pipe from the left side. True means you can get into the pipe from the top. False means you can't get into it from the right, and true here means you can get into it from the bottom. So the path through this pipe is, top to bottom, which means true, and then false and false here and here. And then that same pattern just applies to all of the letters, and that's how we'll determine like the lookup for the direction of the pipes basically. So yeah, that'll determine whether the pipes go vertically, horizontally, or vertically and horizontally, and the direction in each way that they go. And then also what I'm going to do is I'm going to do my map thing that I like to do, where I create a keyed dictionary of the points instead of making a 2D array. I don't really know. I don't think this is actually very advantageous for this problem, because it's not the overall size of the grid isn't where the complexity comes in, so it doesn't really make too much of a difference here. But this is just kind of my default way of doing it. So yeah, with that, I start looping through the file. Take each line of the file, break it up into its characters. So basically I'm trying to pull out the X and Y coordinates for every single point. I record what my start point is, just so that I know when I find the character S in my input, I know exactly what the coordinates for my starting point are. And then aside from that, I just populate the map with all the coordinates. What I do for each symbol that I find is I stick in the corresponding array here that represents that lookup for the directions. I set up a variable here, visited false, which basically means that I have not visited that node yet. We will update that to true as we loop through our map. We'll update that to true for each cell that we end up visiting, and then I just stored the character in there as well, which I don't use in this part, but I'll use it in the second part. You'll see I just stored it. I didn't think I would need to use it, but I just stored it anyway. So the overall answer for this then is where the actual work happens is this recursive call down here. So the answer that gets spat out at the end here is a call to this walk function that I have. You pass in the start point, you pass in the overall map, and you pass in your number of steps, which we initialize to 0. This recursive function runs over and over and over again and spits out some number. In this case, I knew that the number was going to be the half plus 1 to get the right answer, and that worked here, just when you look at the even or oddness of it. So yeah, that was it. That's pretty straightforward. The walking function is where most of the meat of this comes in. So first thing we do when the walk function gets called, we check the node map. We update this. So we've passed in basically a new node, which is our current node we're on. We update that to being visited because we've now been there. If we're back to the start again, so if the current node equals the start node, and we've taken some steps, so this is so that it doesn't just exit immediately, we'll just return the number of steps we have because we've basically done the whole loop and gotten back to the start, and we're done. So the next thing you need to do then as well is you need to look up which steps you need to go. So there's a set of steps that you can go. This is the full set of them. There's only 4 because it's just up, down, left, and right. So we need to check all of those directions because there may be a pipe that goes that way. For the first one, the reason we do this check is because we don't actually know what the directions are. For all the subsequent ones, we actually do know what the direction is, but because I'm doing this with a recursion, you need to build all the logic into the whole thing. So we have our 4 checks down here. So for the first time we execute this, only there'll be 2 paths that are relevant, but then for every other one after this, it'll only be 1 relevant path. So only one of these conditionals will match. And the conditionals are simple. It basically looks at, if we look at the next point of the map, does it exist? So it's not nil. Then we have a look and see, have we visited? So if we've already visited that, then we're not going to visit it again. So we'll skip on to the next one. And then basically we have to try and map the like start and end positions of where we're going. So what this means is that if I'm looking at like a pipe that goes left to right, and then what I'm going into is say also a pipe that goes left to right, I need to look at, well, the rightmost output of this pipe, does that match the leftmost input of that pipe? If that's true, then I know that I can move from that cell to this cell with a pipe in between them. If it wasn't the case, so for example, say the case, so what I just described here is basically this thing here. So you've got 2 dashes. I know that if I'm on the rightmost side of that, the rightmost side of that can move into the leftmost side of this. And then the same would be the case, say, if I had a 7 here. So the rightmost side of that can move into the leftmost side of that. But say if I had what's the other one? An F here. The rightmost side of that cannot move into the leftmost side of this. So that isn't a possible path that I can take. So I wouldn't be able to move down that path. So by looking at the 4 pipe endings all around you, from any one pipe, you'll determine which one you can move to. For the start, there's 2. And for everything else after that, there's only going to be 1. And that's it. So only one of these conditionals will match after that. You may ask, you've got 2, so you're effectively doing it twice. I did fudge this a little bit. So if you scroll all the way up here, I have a special case up here for the start where I look at the table, and you'll notice that I decided that the start only has 1 direction that it can go. In theory, it can go any direction, but I had a look at my input and saw that my S would either move left or right, so I just coded it to be in one direction, and that's it. And that means that you don't end up doing a whole extra loop of this when you don't have to. And yeah, that's it then. So this will loop through the whole thing, and at the end you're basically summing the step count. So you increment the step count each time you call this, and yeah, you just spit it out at the end, and that's it. And I'll give you your answer. This makes a lot of assumptions, this code does. Like at first I was thinking that maybe the pipe network branched, but then I realized that wouldn't be possible because that would mean that there was a point where you could have 2 directions you can travel, but we've basically determined that you can only have 1. So the only place where there's a split in the pipework is that first one, basically. Everything else is just like a one. There's only 1 direction it can go. You just have to determine which exactly that is. And that's it. Yeah, it's not the most elegant solution. It took me a little bit of brain work to actually get through this one. So even for a part 1, this took a fair amount of effort. I also ran into some problems with my recursion. I was running out of stack depth, but I knew it wasn't just an infinite loop. It was just taking a lot of loops to do it. So I had to do a small bit of refactoring and actually had to increase the allocated stack size in Ruby. So yeah, that was something I had to do. But it does work. So if I do run 10.1 on the sample, So it runs 2.18 milliseconds, relatively fast. Not super quick though. And then on my input, yeah, also runs, yeah, not super fast, but yeah, reasonable enough time. Yeah, okay. So that is part 1. Let's have a look at part 2. So part 2 is really what what gave me a bit of a headache. It took me a little bit of a while to arrive at a way that I wanted to solve it, and then once I had that way I wanted to solve it, implementing it just gave me a headache until I discovered just this one little bit that I was kind of missing. So let's have a look at what part 2 is. So for part 2, basically for part 2, what they say is that so you were chasing this animal around the pipework and you never ended up heading them off or finding them or whatever. So you think that maybe their nest, where the animal lives, is somewhere inside this pipe network, so bound inside the area that the pipe network encompasses. And they give you a few examples of what that looks like. So here is a sample network, and you see here you've got dots, which is basically, there's all stuff outside. He highlights here where there's the points that are outside with O's, but then points that are inside, so they're bounded by the pipe network, are these I points here. So there's a whole bunch of different examples of this. More complicated ones down here, where he's got outside points highlighted and inside points highlighted. And basically, yeah, the job is, we've determined what our path is, so we sort of know what the boundary of this like shape is, if we imagine it that way, and we want to determine what the area inside it is and what the area outside it is. Or, well, I mean, it's basically the same thing. Like, so the area inside is what the answer wants, but if you determined the area outside, you could work out the area inside. So algorithmically, there's a few different ways you can solve this. I went with a particular one, which is kind of slightly more maybe of a mathematical one, but there's multiple different ways you can solve this. So, okay, is there anything else to say about this? Yeah, okay, so we talk about the solution. So the first thing that I thought to do was, maybe it was something like you could use the flood fill algorithm to do this, but I didn't really want to implement the flood fill algorithm to solve it. I think you can solve this with flood fill. So basically you need to start at like a seeded point, and then you need to run the algorithm to determine what the bounds of the shape that you're looking at are. So that's one way to do it. Another way to do it is, you could think of this entire shape basically as a polygon. So if you think, you can think about that, and that seems like it doesn't get you very far, but there is a very particular piece of maths that will work for polygons. So there's this quite amazing property which is called like the point inside a polygon thing, which I think is called the ray casting algorithm, something like that, where basically what would be the best way to do this? Yeah, I can actually, I'll show it. Point in polygon. Yeah, point in polygon. Here we go. So this is the best way to look at it, is this demonstration here. So if we imagine our pipe network, the shape that our pipe network traces out is this polygon, the way you can determine if any arbitrary point is inside or outside that polygon is by starting from some point anywhere outside the polygon. It doesn't matter what direction you do this in. For our case, let's say the very left of our whole thing. You iterate through all the points along this line until you hit a crossing point or a boundary point. So you hit that boundary point, so you count that as 1. So you've crossed the boundary of the polygon once. You then move over to the left and you hit that boundary point again, so you count that as 2. And so on and so forth until you get to your final point, which is what the point you're interested in. The trick then is that whether you are inside the polygon or outside the polygon at that point is based on whether you have crossed those boundaries an even or an odd number of times. So that might seem a bit weird, but it is true. I mean, if you thought about this as like just being, say, a circle, for example. As you move from the right, you'll hit the edge of the circle. So then now you're inside the circle. So we've counted one crossing of that boundary. So all along that line then, until you hit another boundary, you're still inside the circle, right? So then when you bump outside that circle, now you've counted two encounters. You've had two encounters with that boundary. So now you know you're outside the circle again. And it's the same with any polygon shape. This will hold true. And for polygons, it works incredibly well when they're, you know, nested all over, like on top of each other and stuff. So same thing happens here. This is a great example of where there's an indent, and so you end up, as you draw your line across, you're crossing this polygon several times, and yeah, that's it. So if we think of our web of pipes as a polygon, we basically need to apply the same rule, and we can get to the correct answer. Easier said than done, though. So, with that said, let's have a look at the code. So, part 2. So, our code is more or less the same for the very start. I set all this stuff up all the same, except that this time I want to pull out two variables. I want to know the maximum x position and the maximum y position, because I'm going to do a dirty two-dimensional loop in here. We go through the same algorithm we did earlier, so we walk the whole path that we did, except this time we're not interested in the number of steps that it spits out. The only reason we want to walk this path is because as we walk that path, we're updating this visited value, which basically gives us a set of points that we know make up the boundary of the whole shape that we're looking at. So that's the only reason we want to do this walk again. The guts of what we need to do then to get our answer is all inside this loop here. So I made a two-dimensional loop here that'll loop through every single point, basically in a grid fashion. And what that will do is it will give me, it will allow me to perform this algorithm that we saw. So I'm doing this in a fairly inefficient way because it was breaking my brain a little bit implementing it. So basically I'm just doing a two-dimensional loop. The first thing I do is I check if those if any point that I hit has been visited or not in my earlier map. If it has been visited, I know it's part of the boundary. If it's part of the boundary, logically I'm saying that counts as being outside of the what's bound by it. So I just basically just update this outside counter. Don't actually even need this outside counter, but it was just useful for me while I was debugging it to keep track of the outside versus inside counts to make sure they'd all add up to the right numbers. This grid thing you can ignore. I just did this. This is for debugging for visual debugging of the samples. It doesn't actually play a part in the actual solution. So I could actually speed up my actual solution if I wasn't messing around with this two-dimensional array. But we did say earlier that a two-dimensional array is kind of fine for this problem because it's not a ridiculously large. It's not a ridiculously large array in the end. So we start from arbitrary x. So we start from the top, very top left, x, y. So we take that first point and we need to check. Basically, is it part of the polygon or not? And so from there, what we do is you go from the very left and you move over, iterating through all the points up to that point, and you see, do I have any crosses? Have I crossed the boundary of the polygon? And then I count that. So that's what this is doing here. So this line here starts from the very left up to whatever the current x position is, and it checks if we crossed the boundary. If we've crossed the boundary, it increments that counter. And then once it's gone from 0 to that x point, we just do a very simple check here. Is it even or is it odd? If it's even, then it's an outside point. We update our grid here to show that, and then the opposite then for if it is inside. And that's it. We do that for every single point, and at the end of it, we'll have our count of insides and our count of outsides. the hardest part of this entire thing, this bit just iterating through every point and doing some check on it, is conceptually super simple. This single line here is what took me the longest to figure out. And basically what this is, this piece of logic, and this is the only piece of logic that you need to know to discover that boundary. So I knew I needed to look for boundaries, but it was determining the boundary that I found the hardest part. So to determine a boundary, the boundary point is going to be, because you're looking at up and down basically, any time you encounter a point that you have visited, so it's part of the overall boundary, and it is vertical, so it either goes up or goes down, that's going to be, you count that as the time, one of the times we've crossed our line. It doesn't matter if it goes up or down. It just has to be, you just have to choose one. Either you're only looking for when it goes up or you're only looking for when it goes down. Choose one of those and choose that it's one you visited. And that's how you increment the counter for that you've crossed a boundary line. That's unintuitive. And it took me a very long time to arrive at this. But that's effectively what does it. So once you've counted all those crosses, obviously you can do your check and then that's the answer. So we can run this. It is not crazy slow either. It executes in a few milliseconds. This is just an output here of the sample 2. So if you have a look at that sample 2, that's basically this one, is it? Yeah, so that outputs this O's and I's map, and the answer is 8 for the sample, which is correct. And then if I run it for my input, it's not going to draw the grid because I didn't think that would be sensible. Gives me the answer. That is my correct answer. Again, it's not super fast, but also I could speed this up by just removing all the grid stuff that's in there. I was only doing that so that I could print that out for debugging on the samples. For the input, doesn't actually help me solve it. It just slows things down a bit. So yeah, it takes a fifth of a second. I'm not winning any awards here for speed, but finally solved the problem and got through it. So yeah, this was a challenging one. There's a lot of little bits and pieces in it. Tricky to parse, some complicated stuff to solve, and then also for me, I just got caught on like 2 things that really slowed down my whole progress on everything. So yeah, this is a difficult one. I'm hoping tomorrow's not as difficult. But yeah, we'll leave it at that for today. Hope this helps someone. And yeah, I will see you guys tomorrow.